Cosmic potential energy. Today we're going cosmic. We're going to be talking about gravitational potential energy. Up until now, I've told you that PE is mgh. We can't use that if we go cosmic. We can't use that in outer space. Why not? I mean, close to the Earth, within, 300 or 400 kilometers, we could probably still get away with it and be close. But if we, for example, want to go to the moon, G is changing. If we want to figure out how much fuel we need to send a rocket to the moon, we cannot use this as our starting point for energy. So we're going to have to go back to the way we first defined work and energy. We said that the area under a force versus distance graph was equal to So here's a blank graph. I'd like you to put an F on the y-axis and a D on the x-axis, and then just draw kind of a generic slanty line. The force is increasing, so we couldn't go force times distance. But now I'm going to actually be even a little more specific. I said the area under a force versus distance graph is work. Right here, put a little point and call it A. Right here, put a little point and call it B. Draw a dotted line straight up from A, draw a dotted line straight up from B, and then kind of shade or color it in. Now, the area between point A and point B is work, but I want to be even more specific. The area between A and B is the work, and if you want to, you can put in brackets energy required to move from A to B. If you're really asking, what are we figuring out? That's how much energy it took to move this object from location A, wherever the heck that was, 2 meters, to location B, wherever the heck that was, 9 meters. That's how much energy was required. And so we're going to start to try and apply this, but instead of moving from A to B horizontally, Kieran, we're going to start to say, what if we move from A to B, moving away from a planet's gravity? So for gravitational force, now on the y-axis, let's put Fg versus separation distance. On the x-axis, let's put R, which would still be in meters. Now, first of all, what would that graph look like? Don't write this down. It would not be a nice straight line. Don't write this down. Really, force is proportional to 1 over r squared, because it's big G, big M, little m over r squared. So I think you've done the reciprocal graph in pre-calculus 12. It would be the reciprocal of a parabola. I'm not going to be that fussy. I'm just going to say, I know what it looks like. This you can write down. It looks kind of like that. Calculus students, we would say, as r approaches infinity, the force approaches 0. As r approaches 0, the force shoots off to infinity. That right there is your black hole explanation. As r is very close to 0, the gravitational force is crazy high. So let's trace this same graph, Fg and r. But now I'd like you to put a point right there, and we're going to call it r Earth. And then we're going to put another point right here. We're going to call it R orb, for orbit. And if I sketch that same curve, and if I again do the dotted line, vertical line thing, that shaded area would be the work required to move a rocket from the surface of the Earth, that's why we started our Earth, up to orbit. Now, all that would do, by the way, is get it to the right height. It would come crashing back down because we haven't yet given it the kinetic energy it needs to stay there. But let's write this down here. So the area is the work, and you can put in brackets energy required to move from our Earth to our orbit. What's the problem with that area? I don't have a formula for the area of a swooshy shape. And believe it or not, that's one of the main reasons calculus was invented. Calculus was invented to find the slope of a curve or to find the area under a curve. And so we can do it with calculus. Most of you are not in calculus. So I'm going to do a little bit of magic and hand waving. We're going to end up with the right answer, even though my method technically is not mathematically valid. It'll get us there. I know, but I just wanted to give you the benefit of the doubt and humor you. Okay? We did start out defining work as force times distance. So I can say the work done against gravity is going to be the force of gravity times, and I'll call the distance r. So work, subscript grav, the work done against gravity, would be the force of gravity times r. But we're going cosmic, so for gravity, I'm not using little m, little g, like physics 11. We're using the cosmic gravity. We get this. Big G, big M, little m, over r squared times r. Oh. Huh. I noticed something. One of the r's cancels with that one. And so this is actually almost the right equation. Except instead of work, let's write potential energy. You can just cross out the W and put a PE if you want. Now, this is cosmic potential energy, how much work you're doing to lift something up. Leave a small space. It's equal to big G, big M, little m, over R. Except we have to add one more thing. I said leave a small space. Negative. What? Negative. Why is it negative? If you were in calculus, I would say it's a negative because it's the integral of a derivative, and the exponent that we're starting out with is a -2, and you add 1 to the exponent, which gives you a -1, then you multiply onto the front of the exponent, which means you'd multiply by negative, and it's negative. But this is the class where nobody has been to calculus. It's nothing to do with inverse. So I'm going to give you a different explanation. Let's suppose that we had a rocket ship, and that rocket ship had enough fuel to get us all the way to the edge of the universe, where there's no gravity. If there's no gravity, will we fall when we shut off our engines? No. If we won't fall, how much potential energy do we have? 0. We're going to define 0 to be out at the edge of the universe. In fact, the phrase I'm going to say is relative to 0 at infinity. So out at the edge of the universe, you have no potential energy because there's no gravity. Now, to get there, you have to do work, which means you must be starting out with less energy than 0 because you're having to add energy. What numbers can you add to and end up with 0? Where must you start out? Negatives. We're going to say relative to 0 at infinity. This is a weird way to think about it. Everything closer than infinity has a negative amount of potential energy. Now, don't panic. As long as you're careful with the equations, all of the signs will take care of themselves. You'll find you get a minus. You'll find you get a minus quite often, which becomes a plus, and you get a positive answer where you're hoping to get a positive answer. You'll get a negative answer where you lose energy. You'll get a positive energy where you need to gain energy. It'll all take care of itself. But the reason that negative is in there is because it's an integral from calculus. I can't use that explanation. It's because we've defined 0 to be out at infinity. So I wrote here, why negative? Out at infinity, at the very edge of the universe, an object would have 0 potential energy since it's not being affected by any gravitational field. It won't fall. And if it won't fall, it has no energy. If our height is less than infinity, we have less potential energy than that. What numbers are less than 0 potential energy? So we use the phrase relative to 0 at infinity. In fact, in the homework, you'll see me often abbreviate it as relative to 0 at, you'll see the RTZI in brackets or something. That's my way of saying to you, Lena, use the cosmic potential energy, not MGH. Basically, if you're in outer space and we cannot use the MGH, and I'll give you almost a 0 if you do. No. We have to use negative big G, big M, little m over R, which is a lot more typing. So, a mass is released from a height of 6,300 kilometers above the Earth. How fast will it be going when it hits the ground if we ignore air resistance? So we can now start to look at asteroid impacts and things like that and calculate how fast they're going to hit the ground. What's this question wanted me to find, Manir? What, fast or speed? Is there a change in height? Is there a change in speed? Is there a yucky, curvy gravitational field that's changing? This is a job for conservation of energy, but I'm going to go cosmic. So I'm going to start out by saying kinetic initial plus potential initial equals kinetic final plus potential final, and they said ignore air resistance so we won't worry about the heat that it burns up with. Okay. And a 3,040 kilogram mass is big enough that part of it might make it down to the ground in real life anyways. So, are any of these 0? It says released, so I'm going to assume that we're starting at rest. Potential energy final would only be 0 if R was 0. Would only be 0 out at the edge of the universe. So sadly, one of the reasons I said to you these questions take a lot of writing is, sadly, if you start on the surface of the Earth or you end on the surface of the Earth, it's not a 0 that can cancel. You have to include it. The only time it'll cancel is if you're out at the edge of the universe at infinity, which we will look at. We're going to get this. Are we in outer space, Spencer? Say yes. So we have to go cosmic. It's going to be negative big G, big M, little m over R initial. There's potential energy initial. Equals a half little m V final squared plus negative big G, big M, little m over R final. Is there a little m in everything? So how fast the object is traveling when it hits the Earth is independent of its mass. How much damage it does is clearly dependent on the mass. So if I wanted to then eventually turn this into, will this wipe out the dinosaurs? Will this make humans extinct? We can run those numbers. But for now, we can say this. This is about where my love for getting things by itself breaks down, because there's just so much typing here. So I'm going to, could I get the V by itself? You know what? Yeah, the amount of effort to do that though, and then square root everything, we're not going to. Instead, I'm going to leave the half V squared sitting where it is. I'm going to move everything else to one side. So the negative big G, big M over R initial drops down like a domino. I'm going to plus the big G, big M over R final. And that's going to equal 0.5 VF squared. I can already see I didn't leave myself anywhere near enough room, but we'll see. Alrighty. What I'm now going to do, Sarah, again, I'm not going to try and get the V by itself. I'm going to type all of this in, get an answer, and then once I get a number on my calculator, I'll divide by 0.5, square root, done. I'm not going to try and finagle this. So we're going to go to the plugging numbers in stage very carefully, because the biggest mistakes I see are typos. Yeah, you want your calculator out. I get negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. The planet is what does not cancel. Our initial. Where are we starting? 6,300 kilometers. First thing I should have said is nice try. 6.300 times 10 to the 6th, I think. If you multiply that by 1,000. Above. So this is not a radius that they gave me. If they had said a radius, that would be nicer. But the fact that they gave me the above, they gave me that distance, I need to add the radius of the Earth in. Yes? So down here, we're going to have the radius of the Earth and 6.3 times 10 to the 6 or 7? I'd like you to check me. Can you go 6,300 times 1,000, please? Is it? So 6, and then how many digits after the first digit? 6. So 10 to the 6th. And now, some of you who have written ahead, I apologize. This is where we're going to get lazy for the purpose of making less mistakes. There's a plus sign. I'm going to write a ditto mark times a ditto mark. Same thing times same thing on the top. Yes? What are you doing? Patience. What's our final? 6.38 times 10 to the actual surface of the Earth. That equals a half V final squared. I want all of you to get your calculators out because I'm going to show you some. Yeah. I can't hear you. I did right there. That's my initial. I don't do physics with kilometers. I never have. And it's an altitude, so I have to add it to the radius of the Earth, right? Okay. Sarah, no yet. No. I want all of you to follow me step by step on your calculator. For a reason. You'll see why in a second. I'm going to go like this. Clear. Negative 6.67, scientific notation button, negative 11. Type that with me. Times 5.98, scientific notation button 24. I can get away without brackets on the top if I use my scientific notation button because it is all one big uber thing on the top. No plus signs. Is there more than one thing on the bottom? Divided by bracket 6.38 scientific notation 6 plus 6.3 scientific notation 6. I want all of you to type that and nothing else. Radius of the Earth plus the altitude. What I'm going to do here, Lena, I'm going to hit enter and I'm going to write that down to about 5 sig figs. And I stupidly ran out of room, so I'm going to go like this. I'm going to write it kind of here. So I have negative 3 point, it's almost pi, but not quite, that's a fluke, 3.1 1456 That's pretty accurate to me. Times 10 to the 1, 2, 3, 4, 5, 6, 7. You okay with that? I'm going to jot that down. Negative 3.14563 times 10 to the 7th. And then right here there's a plus sign. Now, do you all still have this? Nobody's moved ahead. This is why I do it this way. Backspace. Bring this previous expression up. So bring your last line up. Seems to me all I need to do is delete the negative. Yes? And delete the 6.3 times 10 to the 6th. Because that second term is almost identical, it's way faster to backspace and delete than retype that monstrosity. Isn't that the second term? I'll write that to a few sig figs. 6.2518 times 10 to the 1, 2, 3, 4, 5, 6, 7. That equals 0.5 v squared. And you're going to find I'm going to use that trick of ditto marks and backspacing because you're going to notice if we're dealing with potential energy, the final and the initial terms look so close that it's less typing. You good with that, Eric? So I now have, I think all of you hopefully have the 6.25 blah, blah, blah stored on your calculator. Plus negative 3.141563, scientific notation button 7. Yes? You wrote it down, didn't you? And I always go to 5 or 6 sig figs because that guarantees I'll be good to 3 sig figs for sure. That equals 0.5 v squared. I got 31102 blah blah blah. Yes? No? Yeah? Everybody matching me? If you didn't, you made a typo. Then don't make a typo. This equals. Did I make a typo? Okay. So that. This is where you need to tell me these things. So are you matching me or no? So when a bunch of you nodded, that's irritating. Then say no. I've made the mistake. So I'm going to fix it really quickly. 6.2518 sine. Geez, do it. 6.2518 scientific notation 7 plus negative 3.14563 scientific notation button 7. Now I've rounded off, so my first few digits should match yours. Yes? Yeah. That equals a half v squared. Now how will I get the v by itself? Divide by 0.5 or times by 2. Square root. 788 78 80. That's nowhere near the longest question. That's a baby. And there's just no way to shorten this. What I can do, Lena, is by using those ditto marks and having yelled at you last year to get a good calculator and having Kevin finally gotten a good calculator. This, you timed it well because now, do you know how to backspace on yours too? Yes? It's a massive time saver in typing, but also it means if you type the first one right and you're careful, you've eliminated typos in the second term too. Alrighty. Ooh, I don't know how much we're going to get through here. We'll see. I like example. By the way, I like example 1. I like example 1. I like example 1. I like example 1. What else could I ask you in example 1? I could, instead of saying how fast will it hit the ground, I could tell you how fast it hit the ground and ask you what was the initial radius. You get the RI by itself, but I would do that last. Example 2. Matt, what word did I underline? Do you see the word orbit in this question anywhere? All we're calculating right now is this. How much fuel do we need to burn to get this satellite up to the right height of orbit? it's still going to come crashing down. Why? Because it doesn't have any kinetic energy. We haven't given it its orbital speed yet. We'll combine them all in a second. But for now, how much rocket fuel do I need to pack just to get it there? How much work is done in just lifting it up? What does it want me to find? We're going to be using change in potential plus change in kinetic. Why can't I go work equals force times distance? Because the gravitational force is changing the higher you go. Are we in orbit? So, you can make a little note. Since no orbit, our kinetic energy is 0. And we're going to assume we started out at rest. Now, that is not actually correct. None of us are at rest because the Earth is moving. In real life, you actually have the kinetic energy that you have from spinning with the Earth. And this is why you normally want to launch as far south, as close to the equator as you can, because the Earth is spinning the fastest on the equator. Where did the U.S. build their space center? Florida, as far south as they can go. This is why the Russians had such a tough time with their space program, and why to this day their rockets are workhorses, because they don't have the advantage of the Earth's rotation that the U.S. rockets do. Where would the best place to build a rocket launch be? On the equator. That's why Elon Musk is trying to build ships that can launch rockets, because he's thinking, oh, I'll just park a ship in the ocean on the equator and I'll get the full benefit. We're going to assume that we're launching from the North Pole, from Superman's Fortress of Solitude, so that we have the worst case scenario. We don't have any kinetic energy. Otherwise, the questions get yucky. Matt, what's changing anything? So this is going to be PE final minus PE initial. Are we going cosmic here, Matt? So we can't use MGH. It's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. And none of these will be 0 unless we're out at the edge of the universe at infinity. Spencer, are we out at the edge of the universe at infinity? Are we out at the edge of the universe at infinity? Say no! It's meant to be really obvious because it doesn't say out at the edge of the universe at infinity. So are any of these going to be 0? Work equals negative big G 6.67 times 10 to the negative 11. Big M 5.98 times 10 to the 24th. By the way, does the little m cancel this time? Well, there's an m in this term. There's an m in this term. Is there an m in work? No. And that makes sense. It shouldn't cancel. It should take more fuel to put a bigger thing up there. All over. Oh, little m. Sorry, I forgot little m. 1200. Would have been sloppy after I said it didn't cancel. Our final. Up here. What's up here? Well, it's going to be, because again, they gave us a height. It's going to be starting out the radius of the Earth plus the height. There's our final. Oh, what's a minus minus in? This is why I said, as long as you're careful, everything that needs to become positive will become positive. I'm positive. Oh, ready? Look up. Ditto mark times ditto mark times ditto mark. Because, Munir, the top hasn't changed at all, and that's a lot of typing I can save myself. Over our initial surface of the Earth. 6.38 times 10 to the 6th. Alrighty. We get out our calculator. We type very carefully. Negative 6.67, scientific notation button, negative 11, times 5.98 scientific notation button, 24 times 1200 divided by, more than one thing, bracket, 6.38, scientific notation button 6, plus 1.2, scientific notation button 7. What's your final potential energy? Negative that. Negative 2.60413 times 10 to the 10th. Is that correct? Sorry, I should have asked. Has everybody else got 2? I have a minus minus, which is a plus. Backspace. Oh, don't want to hit that. I delete the negative at the very front because it's positive now. I'm positive. And it looks like here, Lena, all I need to get rid of is that little thingy right there. I'm going to argue, Lena, that's way faster, less typing, and just also, as long as you're extra careful typing in the first expression, you're not going to make a mistake on the second one because you're reusing it. Now, please don't make a mistake on the first one and double down. You get 7.50218 times 10 to the 10th. I still have this number stored, and now I can go plus negative. By the way, instead of going plus negative, what could I type instead? Just plain old takeaway. 2.60413 times 10 to the 10th. How much energy is it going to take to get this rocket up there? 4.898. Okay, now I'm going to go to 3 sig figs. This 9 is the third sig fig. Is it going to stay a 9 or get bumped up? So 4.90 times 10 to the 10th. Units, it's work. Joules. And if you then told me how many joules per liter I got from rocket fuel, I can now tell you how many liters of rocket fuel. Oh, problem. Then I would have to figure out how much mass that rocket fuel added and redo the question because now M has changed. Which means I'll get a bigger answer and I'll need more rocket fuel. But if you told me how many joules per liter, I could calculate how much more rocket fuel. Oh, problem. I just added more mass. Ugh. Let me emphasize, Kieran, we have not put anything in orbit yet because you'll notice our kinetic energy is 0, which means you're at rest. Can you stay at orbit if you're at rest? No. So I wrote here, this satellite has no kinetic energy. It's just going to fall back down. To lift an object, that's why I underlined the word lift, we only need to give it, and you can make a little note, negative big G, big M, little m, over R. Cosmic potential energy, not MGH. To put an object in a stable orbit, we need to give it potential and kinetic. I like example 2. I like example 2. I know we just did example 2. I like example 2 again for some reason. I like example 2 again for some reason. I like, okay. Mitra, what's this question asked me to find? Okay. Are we in outer space going cosmic? Then I'm not going to use force times distance. Work is going to be the change in potential plus the change in kinetic. Mitra, are we in orbit? So can we possibly be at rest? So the change in kinetic will not cancel out. I recommend you break this into parts. I recommend you find the change in potential, get an answer to 5 sig figs, find the change in kinetic, get an answer to 5 sig figs, and then add them up. Mitra, what do you want to find first? Change in potential or change in kinetic? Doesn't matter. Okay. Change in potential. Mitra, what's change in anything? and we're cosmic, so it's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over our initial. I do notice there is a minus minus in the middle. What's a minus minus the same as? That's what's going to give us an overall positive answer, because it does take work to put it up there, so we should get a positive answer. So even though we defined 0 to be infinity, and we're doing this all relative to 0 to infinity, we get the answers we want to get, as long as we're careful. No, I don't have to start there. I could start from a space station. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 925. Our final. Did they give me an altitude or a radius? So do I need to add the 6.38 to that? Okay. I can just use that Mitra as is. Apparently I've already added the 6.38 to that. What did you say a minus minus was? A plus? Ditto mark times ditto mark times ditto mark all over. We're starting on the Earth. Yep. Get out your calculators. Although part of me, Kevin, was going, I'd already planned on this lesson at just laughing at you hysterically as your fingers were developing blisters trying to keep up with our typing, but I'm glad you were forced to make the switch. Alrighty. Negative 6.67. 5.98 times 925 divided by 2.6 times 10 to the 7th. You get negative 1.419 times 10 to the 10th? There's a plus sign. Backspace. I delete the negative at the front. And this time, I guess I have to retype the radius, but that's way less work still. 6.38 times 10 to the 6th. Common mistakes. Sometimes kids forget to delete the negative. Well, you'll get a negative here, multiply that by negative 1, and now you've got the positive answer that you always wanted anyways, right? Do you get 5.7829 times 10 to the 10th? No? Yes? So the amount of work just to get it up there, not keep it up there, but just to get it up there, is going to be that number plus negative 1.419 times 10 to the 10th. And I get, and I'm going to write about 4 sig figs or 5 sig figs. This is not my final answer. So I'm going to go 4.3639 times 10 to the 10th. I'm noticing, Mr. Dewick, I'm often getting 10 to the 10th. Typically, the amount of work is going to be in the 10 to the 9th, 10 to the 10th, 10 to the 11th range. Yeah. And they're big numbers. Again, this is why it's so expensive to put stuff in orbit. And we haven't even got into orbit yet. We just got it high enough. What else do we need to figure out, Mitra? The change in kinetic. What's changing anything? I did say that we're going to be launching from the North Pole, from Superman's Fortress of Solitude, so we can assume that initial is 0. But you can see, launching from Florida, say, would be a big advantage. You would calculate how fast the Earth is moving right at that juncture. It's not that tough to do, and you would not be having to start from 0. The other reason they launch from Florida is if something goes wrong, they abort into the Atlantic Ocean. They've got several thousand miles of basically nothing there, so if something goes wrong, I think I told you the other day, the Pacific is the graveyard of used-up satellites. The Atlantic is the graveyard of oops, something went horribly wrong. I think Elon Musk calls them premature disassemblies or something like that is the joke he makes, right? It's not an explosion, it was just a premature disassembly. They'll get disassembled eventually. Mitra, my joy. What is the equation for kinetic energy? That one isn't going to change. Yep. Half mv final squared. Now this v final, if you want to, instead of v final, you can make a little note. It's v orb. Did I give you v orb in the question? Did I need to? Or if you knew the radius, could you now have said gravity is what's pulling me in a circle and found v orb? That's what we're heading towards. 0.5. Which mass? Little m. That's the satellite. Which v? What was it? 3,000. What did I say it was? 3,000. Because I calculated it for you guys. Squared. What's the change in kinetic energy? By the way, little tricks of the trade. I didn't do this, and I should have. Usually when I find the change in potential, I'll put a box around it because there's so much writing on my page, it makes it easier to spot. I'll do the same thing for the change in kinetic because these are the two answers I'm going to use to find the answer. So the change in kinetic is going to be 0.5 times 925 times 3,917 squared. 7.0961 times 10 to the 9. By the way, what takes more energy, getting it up there or keeping it up there? That's why I said to you the other day, the further out you go, the slower you have to travel, the less kinetic energy you use, but it's just not worth doing that because it takes way more to get it further out anyways. So most of our satellites are in low Earth orbit, as low as we can get them. Here we go. Mitra, what did this question want me to find? The work. And we said the work was equal to the change in potential, 4.3639 times 10 to the 10th, plus the change in kinetic, 7.0961 times 10 to the 9th. Takes a lot of work to figure out how much work. So I happen to have this number still stored, so plus 4.3639 times 10 to the 10th. You're kind of seeing why this is where my I love to get the number formula, rewrite things by itself, dies. I could. It's just not worth it because I'm going to be retyping everything twice. I got 5.07 times 10 to the 10th. Joules. Okay. Let's do a little thought experiment here. Suppose we launch a missile from Superman's Fortress of Solitude on the North Pole. We're going to launch it straight up, and we're going to launch it in such a way that we're going to fire all of its fuel at once, and then it's going to coast. So its fuel is used in an initial burst, and as it rises, the only force it experiences is gravity. What happens to the kinetic energy and the orbital potential energy? Let's look at the kinetic energy first. So if you fire all your fuel and now you coast as you go up, what happens to the kinetic energy? Why does it go down? Okay, so no, yes. What happens to your potential energy? Which also makes sense because the total energy you're starting with is the fuel, and that energy is conserved. So if you initially turn it all into kinetic, but then you're losing kinetic, that energy's got to go somewhere, it goes into potential. Correct answer, C? Alrighty. Boy, I like example 4. I like example 4. Example 4 is a nice question. We're going to get there, I hope. I may have to save that for next class, but we'll see. Here they gave me the speed. They're asking me to find the radius. And then they're asking me to find how much work. Okay. How would I find the orbital radius? Did I say orbit? Nate, what? Gravity is what's pulling me in a circle. And then we can write that as big G, big M, little m over r squared equals m. Which version of A am I going to use here? Okay. The little m's cancel. One of the r's cancels. Kyle, what am I trying to find in part A? Where is the remaining r sitting? Under, did you say? Ugh, can't do math with that. Oh, I can multiply it to the top on the right-hand side. Move the v squared down. So I'm going to get this. R orb equals big G, big M over v squared. Let's get that to like 5 sig figs. 6.67 times 10 to the negative 11. More room, Mr. Duick. Change colors, that's why it was overlapping. R orb 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th divided by 4,200. Don't forget the squared. You get 22611,451, blah, 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 blah. I'm going to go 22,611 times 10 to the 1, 2, 3, 4, 5, 6, 7. 2.2611 times 10 to the 7th meters. Alrighty. B. How much work to put it in? How much work to put it in? Which means work is going to be change in potential plus change in kinetic. Spencer, are we in orbit? So is the change in kinetic going to cancel? Only if it says lift it straight up and keep it there. You can imagine if we're lifting it straight up and keeping it there, little invisible angels or leprechauns or something are holding it in place. But to have it stay in a stable orbit, nothing's going to cancel. Spencer, I got to find change in potential and change in kinetic. I can find them both. I'll find them separately. Which one do you want to find? Because we've got potential. What's change in anything? Can we be bold and go straight to the equation? Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Do the m's cancel here? No, 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 no. All right, the change in potential, it's going to be negative 6.67 times 10 to the negative 11. Are we still around the Earth? I think in the homework, once or twice we do the moon, so just make sure you use the correct masses. But since we're on the Earth, 5.98 times 10 to the 24th. I've scrolled down. What was the mass of the satellite? 1,800? And our final is 2.2611 times 10 to the 7th. Once again, I have a minus minus, which is a plus. Ditto mark times ditto mark times ditto mark divided by our initial radius must be the surface of the Earth in this case. Write small. By the way, this is pretty much the longest question, although here I gave you the speed, which makes it a tiny bit easier. Usually I'll give you the radius and you have to find the speed. I'm going to get negative 6.67 scientific notation button, negative 11. .98 scientific notation button. Ooh, I also missed a negative. That would have been a dumb move. 5.98 times 10 to the 24th. That's a 24, Mr. Dewick, not a 44. Times 1800 divided by 2.2611 scientific notation button 7. And I get negative 3.1753 times 10 to the, was it 10th? Then I have a plus sign and a backspace and edit the negative out. .38 times 10 to the 6th. And I get positive 1.1253 times 10 to the 11th. So take this number and subtract or add the negative of 3.1753 scientific notation button 10 8.078 times 10 to the 10th. Is that right so far, folks? Am I done? Oh, no. And what else do I need to find? Okay. The change in kinetic energy is going to be a half mv final squared minus, we said, let's assume we're starting out at rest, launching from Superman's Fortress of Solitude on the North Pole. So it's going to be 0.5 m 1800 4200 squared. Almost missed one there. You get 1.5876 times 10 to the 10th. Alrighty. The final amount of work, it's going to be the change in potential plus the change in kinetic. The two numbers that I wrote in boxes. The change in potential is 8.078 scientific notation 10 plus 1.5876 scientific notation 10, and I get 9.67 scientific notation times 10 to the 10th. Is that a lot of fuel? About $30,000 a pound to put something in orbit right now. Number 1 is fair game. Number 2 is fair game. Number 3 is fair game. You can cross out number 4. You cross out number 5. And cross out number 6. Seven is good. Eight is good. Spencer, sorry, no, 8. Sorry, 9. I circled 9, not 8. 9 is good. Spencer, number 9. Where do we end up? I skipped 8. 9 is good. Spencer, number 9. Where do we end up? So what's my final potential energy? Well, that'll make the question at least a little bit nicer. At least something kind of vaguely kind of sort of cancels. Skip 10. 11 is good. 13 is good. 14 is good. 15 is good. I will have to show you the video on how to build a Death Star on Wednesday.